Let's get started. So today we're covering generative adversarial networks, abbreviated as GANs, G-A-N-S, or G-A-N. Add the S at the end. Okay, so far the only generative model we've covered are variational autoencoders. Again, autoencoders themselves are not inherently generative, right? And when I say generative, I'm not talking about like the traditional Gen AI in terms of like large language models, which output text. I'm talking about generating new data, primarily, well, specifically images, right? The idea of kind of going from like quote unquote nothing, or like some noisy vector and blowing that up into an actual image, right? LLMs don't exactly work with this. They've just kind of been looped in with the whole Gen AI thing. Well, so when I talk about generative models, think more like Dolly or like VO3, like image generation models, right? Okay. So yeah, we've only covered variational autoencoders, and the way those work, roughly, just high level, is that during training, you input a bunch of images from your data set, right? So you input them into something called an encoder, right? And so kind of have the visual of like a neural network. You know how it starts as very broad in the beginning and it gets narrow, narrow, and narrower, right? So that's what an encoder does, right? So it has for an image encoder, it has some CNN layers to, take as input an image, and then it crunches that representation down to a very small sparse vector, right? So this vector might be three-dimensional, right? But, if the original image was 20 by 28 by 3, this new vector might be 5 by 5 by 10 or something, or 5 by 5 by 8, 2 in this case, right? In this case, just 2 by 3, right? And so the encoder is learning how to crunch down images, and the decoder takes one of those crunch down vectors, we call them. So something like this in this 2 by 3 vector, and then takes that and blows it up into a actual image, a new image, ideally, right? And so if you want to generate completely new images, right? After you finish training, so the encoder learns how to crunch down information, and the decoder learns how to blow it back up. Um, so to actually generate new images, you take one of these crunch down vectors or latent representations, which is a formal definition. You pick one, it could be a new one, a brand new one, that's similar to a known image. So for example, if I want to generate a new image of the number 5 that was not on my data set, I would just pick the latent representation, so this 2 by 3 vector of a known number 5. So I just choose a 2 by 3 vector, throw it into the decoder and get a brand new image out, right? So we're going to be talking about a different way of generating new images, called GANs. So GANs like kind of beat out variational autoencoders pretty like badly. If you look at benchmarks, GANs even now are still doing very, very well. Of course, not the vanilla kind of GANs that we'll be talking about, but kind of innovations on GANs have done very well, even up to today, right? So with GANs, we have a generator and a discriminator. So there's two parts to our architecture. And the generator, as the name implies, takes some, again, noisy vector, right? And blows that up into a larger image, right? The discriminator is, again, a separate kind of neural network that takes an image that we just generated and also takes a actual image from the data set, right? So a fake image that we created and a real image, so to speak, from the data set. And its goal is this like classification, right? Is the input image real or fake? Fake as in was it generated or was it from the original data set, right? So in this case, our generator is really bad. It's a pretty crappy 8. So our discriminator can say very confidently, hey, this is not a real image, right? So these two players are how we generate pretty good images, right? But yeah, so before I get more to like the actual architecture, I want to talk a little bit more about the intuition of how GANs work, right? So kind of forget about machine learning for a second and just like imagine you want to learn how to paint like Van Gogh, right? Like paint like him, like copy his art style, right? Problem is you don't know how to paint at all, right? And so, Van Gogh's dead. He can't directly teach you. And let's say you're too broke and you don't have any internet, so you can't like see any of his works, right? So you don't have access to any of his paintings, and he can't come down from the heavens and tell you, oh, I can't tutor you, right? So in this case, let's see, you're not that broke. Your friend's an art appraiser, right? So what you have is yourself, the painter. Your goal is to paint Van Gogh forgeries, right? And then the art appraiser, right? Who alongside you, as you learn to paint, they're also learning how to tell if your painting is a Van Gogh one or not, right? Like there's two players, the art appraiser and the painter, right? So early on in your learning process, right? Again, you don't know how to paint, so you just put scribbles, garbage, right? Um, yeah. So again, you haven't really gotten feedback from the appraiser yet. So again, you've never seen a painting, so it's kind of the best you can do. So the appraiser, again, they're learning with you. They're not a pre-trained expert, so to speak, right? So they take a look at your crappy strokes and they take a look at these full images, and their work's pretty easy, right? I mean, they can pretty easily tell, okay, what is and is not a Van, like what's yours and what's Van Gogh's, very easily, right? Now, note that they don't have to be that good of an appraiser, right? Like maybe if they see a actually good forgery, they might not be able to tell the difference because they're just looking at your pictures and Van Gogh's pictures, right? So once you get a little bit feedback from the appraiser telling you, hey, like, you got to draw actual shapes, right? You start making more concrete paintings. So again, your work's starting to take form, but again, it's not similar to his yet, right? Now the appraiser, right? No, before he was very confident what was and wasn't a Van Gogh painting, right? Like he thought like he was 0.01 percent sure like yours was a Van Gogh painting, right? So effectively sure, like very confident yours were fake, right? But now it's getting a little bit harder for him. A little bit harder, right? Because again, he's learning alongside you what is real and what is fake, right? So pretty soon you can generate actual images, like nice paintings, but they're not quite his art style, right? So now the art appraiser is actually having more of a difficult time, right? Because now he has to learn, okay, what exactly makes a Van Gogh painting versus just some nice, well done artwork, right? So each time the appraiser learns a lesson, right, he kind of relays that back to you. So in this case, so before, right, the appraiser's like, okay, like a Van Gogh painting has actual shapes in it. So that's what he tells you, and you have actual shapes. Now he says, okay, a Van Gogh painting is a painting, not hand-drawn stuff. So you take that and you apply that to your work, right? So each time the appraiser learns something new, they relay that information back to you. So then you improve, and then the appraiser improves. You kind of see this back and forth of your improvements inform the appraiser's, uh, I guess, classification ability, which informs your progress, right? So finally, at the end, you become really good at forgeries, and the appraiser just cannot tell what's real and what's fake. So now you've, but kind of by this problem, you've kind of won, right? You as the painter have won, and you fool the appraiser, right? Okay, so in this kind of analogy, as you can probably guess, the painter is the generator, right? So again, you're learning to generate images, but the key thing here is you're learning to generate them based off of the discriminator's feedback, right? The discriminator is as you're kind of giving it your slowly improving drawings, is learning to tell the difference between the data sets and the fake images. And the hope, again, because at the end of the day, we just want to generate whatever type of image we want, right? So at the end, the hope is that our generator becomes so good that it fools the discriminator. And later on, if I want to generate Van Gogh paintings, I can just throw away the discriminator and I can only use the generator to just make as many paintings as I want, right? So, just again, I'm still just talking about like broad intuition. I'll go more into the specifics a little bit because there's a lot of math involved. But just a little bit more intuition, right? So when we're talking about loss and training, right? So again, the generator and discriminator are two separate neural networks, right? They don't share weights, right? What they do share is they kind of tell each other their losses and therefore their gradients, right? So you can imagine that the generator's gradients, so the direction in which it improves in, right, is roughly proportional to the discriminator's gradient, right? Or really roughly proportional to the inverse of the discriminator's gradient. Remember, the gradient is like, we use it, when I say gradient, I mean like the gradient used in back propagation, right? So the gradient telling, the neural network how to improve its weights and biases and become better at its task, right? So the gradients, right, in the discriminator are pushing it towards becoming a better classifier, right? Again, the generator also fools the classifier, right? So we can kind of take a look at those gradients and maybe move roughly in the opposite direction to learn, okay, I can change my weights in this way to better fool the classifier, right? So the discriminator's loss is way more straightforward, right? This is classic binary cross entropy, or otherwise just the standard classification loss. Again, the discriminator is just your classic CNN-esque image classifier, right? Binary classification. I think this is lecture 4, right? We've seen the discriminators architecture before. So one question you might be asking, right, is why do we train the discriminator alongside the generator? Like, why don't we just have a pre-trained generator, or sorry, discriminator from the get-go? Well, remember the generator, right? The way it trains is by taking a look at the discriminator's gradient slash loss, right? Again, it sees in which direction does the how the discriminator improves, and then kind of does the inverse of that to try to trick the discriminator later on, right? If the discriminator was already like, perfect 100% accuracy from the beginning, right? Well, there's no gradient to use. Your gradients are effectively zero. There's nothing for the generator to train with. So in the long run, this will result in a vanishing gradient. So in other words, for the generator, right? So I'll go more into the math in a little bit, but does that intuition make sense? Okay. And again, a little bit more in terms of the architecture, what these look like. Again, the discriminator, just a CNN, right? It's just a CNN. There's nothing more to it. Outputting a number between 0 and 1. 1 being, hey, I 100% believe that this image is real. This image is from the data set. That's what a 1 means, right? 100% probability. 0 meaning, hey, I think this is fake. The generator created this image. So the generator is the encoder bit from an autoencoder, right? So in other words, sorry, backwards. The decoder bit from an autoencoder, right? So it takes some random vector, right? And then it does something called transpose convolutions. So remember convolutions, right? Like normal convolutions, they slide through an image and kind of summarize whatever's in that window, right? So if you're not careful, right, by adding padding, convolutions shrink an image, right? Transpose convolution do the opposite. The upscale an image, right? And I'll go through how those work in a little bit. But essentially, you're upscaling that vector until you get an actual image. So again, like a standard convolution, a transpose convolution has a kernel, right? So remember, kernels are learned, right? So you might, in this case, our kernel, like the kernel size is fixed. So we have a 2 by 2 kernel, but the values in them, again, are learned, right? And so you can think of the kernel as like, they're learning how to best upscale an image, right? So just as the CNN learned, like the elements in a convolution, sorry, are like kind of act as a learned filter, extracting what's important from an image. The kernel in a transpose convolution are learning how to best upscale that image, right? So the input is also a window from the original image or vector that's the same size as the kernel, and the output is some upscaled uh, grid, right? And so the amount that like the output size is determined by your stride, which I'll get to in a second. Oh, I guess I did not get into that second. Sorry, we covered transpose convolutions like I think pretty thoroughly in the last lecture, which a lot of you were not here for. But essentially, in this case, we have a 3 by 3 output because the kernel has a stride of 1, right? So if it had a stride of 2, the output would be 4 by 4, and so on and so forth. Remember, stride is how much that kernel slides across the inputs. Um, so yeah. Uh, yeah. At the end, I guess I can go through transpose convolutions from the previous lecture if you guys want to stick around for that. But again, just think of transpose convolution as a learned way of upscaling an image. Sound good? Okay. Thank you for your patience. Yeah. So again, we're still kind of talking about intuition, or we've talked about the architecture, roughly how this thing trains, right? So again, they take turns during the training, right? So you can imagine that the generator might start first, for example, right? Outputting crappy images of just noise, right? And the discriminator takes that synthetic data set of what the generator created, takes a look at the real data set, and then learns a classification problem, right? So while the discriminator is learning, the generator is not learning, and vice versa, right? So they kind of take turns training. Um, yeah, what's important though is we don't want the discriminator to converge, right? So while the generator is outputting its crappy images, we don't want it to become super like confident quite yet. So we might fix the number of times it trains. So maybe like discriminator does like 200 epochs, right? And then we stop it before it gets too good. We go back to the generator, right? We don't want the discriminator to like spend too much time overfitting to like crappy data. If that makes sense. And again, we'll get through a little bit more of that later. But yeah. Okay, I want to go through like some probability and math in a little bit, but I want to make sure you guys all understand the intuition. Any questions yet? I know we had some people come in late, so if you have any questions about earlier stuff, that's fine too.
But that never sees from data set generator. So
Yeah.
which it gets the like the one that it gave to the discriminator.
Yeah, so generator never really sees images, right? All it does is output images. So the generator takes like randomly sampled vectors, again, like random vectors, right? So in this case, 1D vectors, right? And it learns how to blow up those vectors into an actual image. The discriminator is the one that's actually seeing, uh, you know, images the generator made and images from the data set. The generator just doesn't see any of that. Does that make sense?
Yeah, so the vectors come from the
No, no, no. The vectors you might just randomly sample from like a bell curve or some probability distribution. No, no, like for example, like in this case, I have a 4D vector, right? So each of these numbers were randomly picked. So the 0.1 was picked from like a normal distribution or like a random number generator. So each of these numbers were randomly picked. So the generator is learning how to go from like literally random numbers to an actual image. So in reality, the way GANs work is like you could probably imagine like there is some structure to picking these random numbers, to sampling these numbers, but for now, that's the intuition, like just literally random numbers to an image. Okay, yeah, good question. Anything else? Okay, yeah. So we're gonna take a lot of steps back, right? Yeah, go for it.
This might be a weird question, but could you go back to the slide where it's showing the model? Could you say take that randomly sampled vector and make that mean something like a prompt, so that way you can have it be really good at responding to the prompts?
I see where you're going with this. Sort of. Yeah. You could inform, yeah, you could bias these numbers towards a kind of prompt. I get what you're saying. Yeah, yeah, yeah. So that's an insightful question. So we don't have time. Diffusion models do a lot of that, and are really good at doing that. GANs not as much, and you'll see a little bit why. But that's kind of we actually don't. I actually don't get into those in the diffusion lecture either. But maybe in a future lecture, I'll cover like uh, diffusion models that do both image and text inputs. Very insightful question. Okay, anything else? Okay, so I just want to kind of redefine a little bit how we think of a data set, right? So again, if we want a model, right, GAN or not GAN, to generate numbers, right, we kind of start by thinking of all the possible images in the world or the universe, really, right? And just label them as are they a number or are they not a number, right? So in this case, it's pretty easy. I have some images up here, right? So it's a binary, right? Either this is what we want or this is not what we want, right? So if we were to kind of take all those possible images of really all images, our domain is all possible images that could be constructed, that have been constructed, right? Just all possible combinations of 256 by 256 by 3, right? If you were to plot them all, right, you can imagine that, if we had a little bit of graph, we put spikes or like, the question is, should our model predict this, right? We could put spikes everywhere where, yay, we do want to predict this, right? And kind of, okay, this should be flat, but really like anywhere flat, right? Where uh, we don't want to predict it, right? So you could say, okay, why make this continuous? Or why don't I just put a dot everywhere I want, right? I didn't have the space to make this look continuous. In reality, right, like, I'm kind of smushing this to a 2D visualization, but you can imagine every single pixel is its own degree, is its own axis, right? So you can imagine that highly visually similar images are like nearby each other in whatever coordinate plane we have. Does that make sense? So that's why we're kind of using this continuous representation, because some images, right, might really look like numbers, or like maybe it's like a number that's like a poorly drawn number. So you might kind of want to put that in, right? But anyways, we benefit more from a continuous representation. So if we wanted to kind of back to kind of constructing a data set, right? You could imagine that it might be easier for us to look at this curve if we were to call this like a probability curve, right? So that is, again, we're still kind of defining functions here. So we could say that any image that has a spike as in a positive probability, that means like, we want with that amount of probability to generate that image, right? So for example, if two images have the same peaks, right? That means with equal probability, we want to generate both images. So the 5 and 8 equal probability we want to generate. 5, 8, and 7, right? So if one image has a higher probability than another, so x sub I, x1, x2, x just refers to an image, right? That's the variable like x is sampled from this uh, image data set, or sorry, image domain, right? So if the probability is 0, like it is for most of these images, then we do not want them in our data set, right? So again, right now, we want, we're kind of doing a binary, right? Do we want this image or do we not want this image? So anything with a yes has an equal probability. We want to have an equal probability of being sampled, right? Okay, so now here's where we need a data set, right? Because obviously we cannot look at all images that could be created. They're just not computationally feasible, right? So instead, if P, right, is kind of the true population, right? Like we want our model to generate something from this curve, right? Of all possible known images of numbers, right? Of course, we don't have access to this curve. We never will, right? Instead, we could try to approximate that curve with a data set, right? So a data set is, well, a sample of all possible images we would like to generate, right? So in this case, it's not a bad approximation, right? I mean, we only have 3 images that we want to generate from here. Uh, but again, you could maybe start to understand the importance of of having a lot of samples in your data set, right? Because the fewer samples you have, the less spikes you're going to have in P data, right? And the less P data is going to look like P, or the true data set, or sorry, the true set of images you want. Does that make sense? You want P data to be an approximation, and to have a good approximation, you need a ton of samples, right? So, okay, what we more in terms of what we want, right, is our generator will generate images with some probability, right? And so we want the images that the generator can outputs, right? So P generated being the probability of the generator outputting a certain image, right? So we want PG, the probability of a generator creating an image, to align roughly with P, which we don't have. So really, we align P of G with P data, right? So it's kind of twice removed in a sense, right? Because P of G, we want it to approximate P. At best, it can approximate P of D, right? Um, yeah, I know I'm having a lot of P's and probability. Is this clear what's kind of going on the screen? If not, it's gonna get more confusing. So if this is not clear, please let me know now. You good? Again, spike just means P of G having a spike means there's that amount of probability the generator will produce that image, right? Okay, so question is, how can we learn like what's the strategy of learning P of G, a good P of G, right? Well, there's kind of 2 ways of going about this, right? So one way is taking a look at P data, right? And just doing your best to match it. So almost like a supervised learning problem, like a standard supervised learning problem, right? Where you take a look at P of data, see where all the spikes are, and try to have your generator have spikes in the same places, right? And that's intuitively what a variational autoencoder does. Remember, with VAEs, variational autoencoders, you're taking as input a bunch of images, right? Like you're learning to encode and then decode your entire data set. And then once you're done doing that encoding, decoding process on inference, you sample somewhere where there's a spike, and then boom, you get a new image, right? So at best, VAEs can approximate their data sets, right? At best, they can approximate P data, which itself is approximation of P. What GANs do is a very different approach, right? So instead, we learn which images should have positive probabilities, right? So in other words, right? Again, the generator in a GAN never sees like the data set's images in the data set, sorry, right? So it just keeps outputting images from anywhere along the image domain. And the discriminator says, okay, this should have a positive probability, or this should have a probability of 0, right? So again, a VAE is taking a look at P data, right, and putting spikes there. It's learning to approximate P data, right? What a GAN does is it samples a bunch of X's, a bunch of images, right? And then not necessarily from the data set, and it learns to assign those either positive or no probability. It's kind of a different way of approaching things. Okay. So again, GANs argued the second way of taking a bunch of images and throwing a bunch of stuff at the board and hoping one of them is real. GANs argue that's a better way of approximating P data. Okay. Well, really, sorry, not P data, of approximating P, really. GANs do a better job of approximating P than P data. Okay. Yeah, so again, just review, right? So if a generator outputs something, right? So you can imagine the generator is very early on in trading. If it generates this crappy image, right? That means it sampled this from somewhere in our image domain and it's assigned it a spike. It's given it a high probability, right? It's a discriminator's job to then take a look at that crappy image and be like, no, that should not have a positive probability. That should have a probability of 0, right? And at the same time, the discriminator, to kind of know how to do that, right? Tell right from wrong, takes a look at P data, right? The discriminator takes a look at P data and learns to assign those with high probabilities. Okay, so yeah, so a little bit more in terms of that random vector we were talking about, right? So yeah, in reality, right? Um, like how do we actually pick that random vector? So actually, I talk about that a little bit, right? So what we want to do, right, is again go from a random vector to an actual image, right? So you can imagine that D of Z is kind of a bell curve of just literally numbers, like meaningless, not meaningless, but mostly meaningless numbers, right? We want to sample from those mostly meaningless numbers, construct a vector, and then somehow go from those dots to an actual image, right? That's the goal, right? So again, Z, kind of the input, Z is like our random noise vector, right, that we input into the generator, right? So we sample each element from Z from a different, or not really, from a independent normal distribution, right? And so again, the generator's job is to take those samples in blue and blow them up into actual numbers or images of whatever we want, right? So a little bit more terminology, right? So this squiggly sign here means sampled from, right? So when I see Z squiggly P of Z, that means this latent vector, remember that's a term from autoencoders, this vector, which we'll call a latent, when I say noise vector, I mean a latent vector, is sampled from a bunch of probability distributions, being P sub V, P of V, right? And then so the generator, so we'll treat the generator as almost like a function, or really just a function. So the generator, big G, takes as inputs one of these latent vectors, which again, a vector of random numbers, and then outputs an image X, right? Where X is from P of G. Remember P of G being that probability distribution of all possible images the generator can create, right? Okay. We went through some possibly confusing stuff. Any questions about what's going on? So we sample a noise vector, right, from a bunch of normal distributions, right? So each element of Z was sampled from a normal distribution, right? Once we construct that vector, we throw it through a generator and then hopefully output an actual image. So when I say Z, I mean one of those noisy latent vectors, right? When I say X, I mean a actual image. And just terminology, because there's gonna be a lot of equations using these in a little bit. Okay, so sorry, I know it's kind of jarring, just text. But okay, moving back to the discriminator, which again is just a classifier, and classifiers require labels, right? Again, standard supervised learning problem. So what are the ground truths for the discriminator then, right? Well, obviously images from the data set, right? So if X, again, if an image is from P data or from the data set, right, it is real, the discriminator should give it a probability of 1, which means it should think it's real with 100% confidence. If an image X is from P of G, from the generator, it's fake, obviously, and we want the discriminator to give it a 0 confidence, like 0% confident it's real, right? Okay, so make sure you guys are following along in lieu of having a Kahoot, sorry. I had a Kahoot last time, but I didn't have time to make it for this one. Sorry. Okay. So if X is from P of G, what is the probability of the label Y being 1 if our discriminator is behaving correctly? Yes, Shazam. uh, Conversely, so if X is from P of G, what's the probability of the label being Y being 0? Yeah, great. And then same set of questions for P of data, right? Okay, so again, more terminology, but this is just formalizing what we just said earlier, right? So P sub C, right? Think of that as like the classification, right? So raise your hand if you're taking probability. All right, don't worry. I'll walk you guys through this. Don't worry about it too much, okay? So again, I'm introducing a new probability distribution, P sub C, but think of this as kind of very similar to P's data, very similar to the data set, right? So essentially, what this is the probability that Y, again, the label's only one or zero in this case, right? One being real, zero being fake, right? So the probability that a label, given some image, right? So given an image, right? What is the probability of it being real, right? So again, given X some image. So when I say given, that's where that bar means. So the bar means given. So given X, what is the probability of X's label being one, right? Well, we know this, right? So because we know where X came from, right? So if X is from P data, sorry, that should P real. When I say P real, I mean P data. Sorry. Uh, yeah. So if X is from P data, we know that its real, its label should be one. If X is from P of G, well, we know that its label should be zero, right? And then same with the opposite, right? So, uh, you know, given an image, and we know where it came from, what's the probability that its label is zero? Well, again, we know this, right? We just look at where it came from, right? Pretty simple. So we're comparing this P of C is kind of a ground truth distribution, right? We know this very easily. We're comparing that with P D, which is the discriminator's probability, right? So again, with the discriminator, it looks like the same thing, right? So given an image, right? What is the probability that the discriminator has the output Y? So what is the probability that the discriminator either outputs a one or a zero, right? D of X is just, the discriminator's direct output. Remember, the discriminator outputs a probability, right? Something between zero and one, right? Um, so if the image is real, well, we just take d of x, right? If the image is fake, it's 1 minus d of x, right? So again, does that make sense? Okay, again, this is same ideas from here. We're just formalizing this into actual probabilities. Okay, so we can finally start talking about our objective here, our loss function, right? So, Shazabe and I forgot who else was here from various autoencoders. You'll remember this KL divergence, right? The Kullback-Leibler divergence, right? So essentially, it takes two probabilities, right? So again, our P of C, kind of our ground truth probability distribution, and the probability distribution from our discriminator. It takes these two distributions and compares how similar are they, right? So if they're very similar, our KL divergence is low, right? If they're very different, if the two probability distributions are different, then our divergence is high, right? So these two P and Q, for example, distributions P and Q, right? They look very different, like visually, right? So you can imagine they have a very high KL divergence, right? So how is this actually calculated? Well, again, raise your hand if you know what a summation is or you've seen this term before. Okay, okay. So essentially, a summation is just a sum, right? So we take it's just a for loop, actually. You guys all know what for loops are, right? Yay. A summation is literally just a for loop where you sum all the elements. That's all it is, right? So again, a summation is discrete, right? So for each y, so for each, sorry, elements, really, yeah. So for each label we get, we take the log difference for that image of our of that image from our ground truth compared discriminator. So again, this is division, right? So remember, we're taking the log of two terms divided with each other, right? If you remember your log rules, right? Log of some p of x minus log of q of x is equal to the log of their quotients, right? So this division, you could just intuitively understand this as actually a subtraction. Does that make sense? This is a difference. We're calculating a difference here, right? So again, so for at every image or at every point, discrete point we have in our data set, or sorry, uh, not data, well, yeah, data set and synthetic image, just every point we have, right? We calculate the log difference and then scale that by its probability in the ground truth, right? So, I have kind of an example here if you guys want to like maybe go back in the lecture and play around with it. So again, I have two terms, right? A and B, right? So imagine A and B as the outputs of where we sample our probability distribution, right? So you can imagine if these two are very similar. Yeah. So if A and B, right? So the outputs of our two distribution, if they're similar at the same point, the point being 0.01, right? Then our divergence at that point is 0. Whereas if they're different, right? Well, that divergence goes up, right? But notice it's scaled by A, right? So if A itself has a low probability, then the entire term is scaled down, right? Yeah. So you can imagine this is like almost in terms of importance, right? So the more importance A is, or the higher its probability distribution is, the more, the higher, if there is a difference, the more that, oh, sorry, the more that difference is scaled, right? The more important A is, the more it scales that divergence. The less important A is, even if there's a massive divergence, what the fuck? Oh, yeah, that's from the other room. Because we get background music, right? She's hitting that shit. Um, sorry. So you can see like there's a massive difference between A and B right now. She's not hitting that shit. Um, you see there's a huge difference between these two, right? But the divergence is not that high because A itself is not that high. Versus, right? If A, comparatively the divergence is lower than it was, like the difference was lower than it was before, but because A is so much higher, that divergence is a lot higher as well. But yeah, it's okay. So remember, A and B are probabilities, right? So they can only be positive. If we try one of them to be negative, you get undefined, right? Does anyone know why it becomes undefined? Remember, we're putting this through a log, right? So log negative number, sorry. You raise your hand, but yeah, log negative number, undefined. Okay. So it works actually pretty conveniently for us, right? Because these P stuffs, PCs, PDs, they're probabilities, right? Between 0 and 1. Okay. So for example, right, if this is our PC, right, the orange is our PC, right? So the ground truth, right? We have very nice even spikes where they should be. PD is way wonky. You think early on in training, right, of our discriminator. There's a high KL divergence, right? And during training, right, as training continues, we want a very low KL divergence, right? So by lowering the KL divergence, that means our two terms are very similar to each other, right? But again, this again, we're talking about training the discriminator, right? So to train this discriminator, that means we have to somehow sample a bunch of images, um, like from kind of our domain of images, which becomes really hard, right? So uh, instead of calculating this outright, which is a very hard thing to do, so I have some algebra that simplifies the calculation, right? We can reduce it to this, which might look worse, but it promised me it's way simpler. And this fits perfectly into the structure of a GAN, right? So again, we can reframe this KL divergence, the loss of a discriminator, into this term that captures the relation between the generator and the discriminator, right? So again, if you kind of curious about how I went from KL divergence to this, I'll talk about after class. Okay, so kind of explain what we have here, right? Again, the KL divergence between the ground truth and the discriminator is equal to this, right? So first, this E term is the expectation. And the expectation is an average that you just think of it as an average, right? So again, if you have a bunch of different terms, the expectation is the average over them, right? It's a little bit of a simplification, but mathematically in this case, that's what it's doing, right? So to kind of break this down more, remember we have that squiggly sign again, right? That means X, again, our image is sampled from P data, right? So what we're doing is for each X, right? So for each image sampled in P data, right? We're taking the log of the discriminator's confidence that it's a real image, right? So again, we're doing this for every single image in the data set, right? We take the log of that, and for all of those log discriminators confidences, we just average them together. Right? And again, we take the negative of that, but I'll go into that a little bit, right? So that's this first term. The second term is again, this time we're sampling from all the generators outputs, right? And so we do 1 minus the discriminator's confidence that it's real, right? And we average over all those log probabilities, right? And so we then subtract, take the negative of this term, take the negative of that term, add them up, right? So yeah, so remember, if an image is fake, right? Well, first, sorry, let me backtrack a little bit. This is a loss function, right? We want to minimize this, right? So let me actually move up a little bit, right? So I visualized minus log x, but yeah. Yeah, sorry. Essentially with the minus log, right? If we minimize the minus log of some x, some element x, that's equivalent to maximizing x, right? So if we modify x such that minus log of x is minimized, that's equivalent to maximizing x. Does that make sense? Right? So that's kind of what this graph is showing, right? As we as we follow this curve, as x is maximized, right? You see that the curve decreases, right? So the other way of looking at it is as we follow this curve, x is maximized, despite the log itself decreasing. It should be minus log of x. I don't know. It's possible. Anyways, so why is this significant? Why do we care, right? Remember, the discriminator wants to get really good at classifying images from the dataset correctly, right? So if we minimize, right, the average of its log confidences, right? So if we're minimizing this term, so minus averages of all of our log probabilities, right? That means we're maximizing the average of our probabilities. So we're maximizing the probability that a discriminator thinks images X from the dataset are real. Does that make sense? So by minimizing this loss function, we're increasing the chance that a discriminator outputs a real or sees a fake image and says it's real. Sorry, sees a real image and thinks it's real, right? And then it's the flip side for a fake image, right? Again, what we want, right, is for the discriminator to see a fake image and say it's fake, right? So, the discriminator will see a fake image, hopefully output something close to 0, right? And so by outputting something close to 0, this becomes log of something close to 1, right? And again, by minimizing this log term, right, we're increasing the chance of the discriminator having a low confidence for an image from the generator. Does that make sense? So again, by minimizing this entire equation, we want to maximize d of x for real images, and we're minimizing d of x for fake images, just by minimizing the single loss function. And that's kind of, this loss function kind of describes the entire optimization problem for GANs. Okay. Again, so this 1 minus 0 is what's going on here, right? Oh, sorry, I skipped a slide. Yeah. Okay. Right. So, okay, keep that d of x on this right-hand side in your mind, right? Because I'm going to swap it out with a different term, right? Again, d of x with x being from p of g, right? So I've swapped out that x with g of z, with z being from our latent representation thing, right? So remember, so again, that's the only change I've made, right? So remember, g of z is like one of those random noise vectors, right? So g of z is equivalent to x. So when I say g of z, that means it's an image, right, output by the generator. And the image output from the generator is sampled from this P of G distribution, right? So g of z and x in this equation are equivalent, right? So I swapped it out with the z term, right? Because now this becomes more faithful to like how GANs actually works, right? Because we really sample this noise vector z and then create our image x, which is g of z. Yeah. Okay. Okay, so again, we just covered the loss of our discriminator, right? So this is the loss of our discriminator up here, right? So what is the loss of our generator, right? Well, that's why I was kind of glazing this equation, right? Because it's very elegant, right? So again, the generator only operates, So if you look down here, right? The generator, there's no generator term in this left-hand side. And this left-hand side is the discriminator looking at something from the data set and seeing if it's real or fake. The generator is not involved in this process, right? So from an optimization standpoint, if we're thinking about the gradients of z with respect to something or the generator with respect to something, this term will zero out. That leaves us with this term, right? So we could reuse the same loss almost, right? And get the loss function for our generator, right? Which is just the second term. So you might see in a lot of literature, the loss of the generator is just the minus, the negative of the loss of the discriminator, which is true because remember, the losses are used in backpropagation, and in backpropagation, this term will just zero out. Does that make sense? So the generator and the discriminator have the same loss function, they're just inverted. Right? So you could leave this term in your code, right? Well, usually you would leave this term in your code, right? For the generator, and nothing would break. So they both have the same loss function, they're just inverted. Is that clear? Perfect. Yay. Okay. So a little bit more into this intuition. So you can think of this as like a min-max game in game theory, right? So essentially the generator, right, essentially wants to minimize our value function being v, while the discriminator wants to maximize our value function, right? Honestly, I think it's a little bit convoluted, honestly. I don't have to get into the game theory stuff that much. I'm not gonna lie. Do you guys want to, like, is it clear at this point what's going on? All right, because this is just like another analogy in case you guys are confused. But okay, if y'all are good, then I can just skip through this. Yeah, you could just think of it as like what's important is like they're adversarial. That's where you generate adversarial networks, right? Because again, um, if this is our loss, right? The generator is optimizing for the negative of this, whereas the discriminator is optimizing for this itself, so the positive of this element, right? So they're moving in two different directions. If like each term in our gain, you can think of it, the generator does its best to confuse the discriminator, and the discriminator does its best to like beat the generator and like find its tricks and stuff. So again, they're adversarial in that way, right? Okay. Okay, so more onto like actually training it, right? So again, I have a bunch of the probability distributions here. In Orange, we have P data. This is not changing at all, right? This is just kind of our data set, right? It doesn't change. Early on in training, right? Again, they take turns training. So the generator starts. You can imagine the generator only has spikes and random noise, right? Because the generator is just presenting the discriminator with images and it's saying, hey, is this real or fake, right? So at first, those random images will be random images, completely random from noise, right? The discriminator at this point is not that good. You could think of it as like completely random. You could assume at this point the discriminator has like trained a little bit, maybe. I say it hasn't trained, but maybe it's like kind of good, right? It has a somewhat positive probability here, more negative probability here, right? But after it does train, so generator just outputs a bunch of garbage image. I say it's training, but really just outputting garbage images. It has no gradient signal yet, right? So after the generator outputs a bunch of stuff, noise in this case, the discriminator now actually trains. It sees the images in P of data, and it sees the discriminator images, sorry, the generated images, and does the easiest thing. It's just, directly makes these zero or close to zero, the generated images, and the real images, it just directly assigns as a positive probability. So you can imagine all the stuff in the middle, these unseen images, might also have like positive or zero, like they kind of have undefined behavior, right? So you'll notice, right, that, okay, as the generator is now, the discriminator is kind of beating it out. It knows what's real and fake. But afterwards, the generator takes that signal, right, and then optimizes in the, in that direction. And now it gets closer and closer to P data, right? So now the generator is effectively fooling this frozen discriminator, right? So as the discriminator is right now, so you can see this blue curve is well inside this pink curve, right? So because the generator is fooling the discriminator at this point, it has to continue training and get smarter and smarter until it kind of kicks out that distribution, right? There's less of an overlap. And we keep training until the generator cannot tell the difference, right? And we hope by this point in training that P of G and P of D, so the images the generator can generate, the images from our data set, they are indistinguishable to our discriminator at this point, right? Okay, So that's just kind of the rough structure of training a GANs. Is there any question about that? So we've already seen the architecture, right? So some decoder S architecture for the generator, CNN architecture for the discriminator, right? And then literally the objective function is what we saw before, those two expectations. And if you just do your standard backpropagation with that loss function, hopefully you'll get this behavior. We have a bunch of problems that we'll cover, but um, that's kind of how it happens. Just
So
like,
you said, you said that you would maybe train discriminating like 200 bucks just to avoid overfitting.
opposite. So we don't want to train the discriminator too long because like if we overfit the discriminator, um, we'll get a vanishing gradient for the generator. So and I'll cover that exact thing in a little bit. Yeah.
PG and PG. Adjust one default.
That's a good question. So epochs are a little bit confusing in this case. So I think in my slides, I kind of okay. So in my slides, I have like first, while the generator is training, the discriminator is not training. So they're frozen, right? So again, that makes sense, right? Because the discriminator creates almost like a fake data set from the generator's outputs, right? If the generator is changing as it's creating those data set images, the discriminator is not gonna be able to train very well, right? So they're frozen. So you train one, you freeze the other, right? How you define an epoch is really up to you. I've seen people like, I think the convention actually is to like, one epoch involves training both of them. So like generator first, discriminator second, and that's one epoch. I've seen like less commonly epoch one is generator, or even epochs is generator, odd epochs are discriminator. The important part is one is frozen, one the other is trained. Anything else? Good questions, by the way. Okay. I'll keep moving. So first goes back to Shazab's question and answers the question, why can't we just pre-train a discriminator? Why can't we just have the best possible discriminator? Like if we're generating MNIST images, like hand-drawn images that we saw before, right? Why can't we just have the best possible classifier? Won't that make a really smart generator, right? Another problem is this dynamic between like this adversarial dynamic, the generator trying to fool the discriminator and the discriminator trying to catch up with the generator. This, theoretically at least, is not always guaranteed to converge. So that's another issue. And the third one, the most famous one, I believe, is mode collapse. Okay, so first, the question of why don't we have, so in other words, the probability distribution, P of D equal PSE, meaning that the discriminator is just a ground truth, right? Because in theory, when we think of classifiers, right? If the classifier on our test set we don't even have a test set. So if the classifier, can output everything in our data set with 100% confidence as real and everything else is fake, that's a good classifier, right? Conventionally, when we think of image classification, right? So what happens if we put this best classifier, which I have in quotation marks? So this is our best classifier, right? 100% accuracy classifier. What happens if we plug this into our loss function, right? Well, what happens is that the loss of our discriminator just becomes like a constant or zero, right? So again, this loss up here, right? So if our discriminator is perfect, it has 100% accuracy, right? So this term, what will this term become? If the discriminator always guesses everything right with 100% confidence, 1, yeah. This term will become 1. It'll see each image in the real data set and be like, hey, this is a real image with 100% confidence. The average of a bunch of ones is 1, right? It'll see everything in the fake data set and be, hey, this is 0. So this loss will be a constant, right? But remember, if this is constant, then the gradient of that constant is 0. So boom, our gradients vanish, right? So that's why we don't want our discriminator to be perfect. If it's perfect, then we can't train, right? At least if it's perfect from the get-go. Can't be perfect from epoch 0. So what's actually the optimal discriminator? So when I now say optimal, I mean optimal for training a good GAN model, for optimal for having a smart generator, right? What's optimal is if by the end of training, our discriminator kind of has this behavior, right? So in other words, the probability of X, right? Um, so the probability that X is real, right? Is just like the number of real images over the number of fake images. So in other words, if there are 50-50 real and fake images, the generator should always output a 0.5. In other words, it should always be confused, right? At the end of training, like um, an optimal discriminator will be confused. It won't be able to tell the difference. Again, if our discriminator is ever 100% confident of what's real and fake, right? The moment that happens, we stop training because we have zero gradients. Or like we're forced to stop training, sorry, right? Because zero gradients, no training. If our gradient, or sorry, if our discriminator instead, right, our generator becomes really smart, our discriminator is always confused. That means, hey, we could, we never have those zeroed out gradients. So you guys understand like the difference between a best, as in like 100% accuracy classifier, versus a optimal classifier. Whoa, that's a bad standard. Versus the optimal classifier that's best for training our GANs. All right, perfect. Okay. I just talked about this kind of. Okay, so there's two ways of preventing our discriminator from reaching that really high accuracy. One is when the discriminator gets to train, we just manually pick how many epochs it can train for and just, don't let it train for too long, right? Manually set some number of epochs where like, hey, in 50 epochs, it could roughly learn the difference between real and fake, but not with super high accuracy, right? Another way is by having the learning rate of the discriminator should be larger than yeah, be larger than the generator. So yeah. So this forces the discriminator to train faster. And yeah. Oh yeah. Sorry. I was like, what this? Yeah, because this is counterintuitive, right? Um, if the whole point is we don't want the discriminator to be too good, why would we want the learning for the discriminator to be higher than that of the generator, right? Well, the the reason why we want this is again, if we stop training too early, we might just end up with a really bad discriminator. And if we have a bad discriminator, we have a bad generator. So it's tricky, right? Because we want the discriminator to be good enough, right? But not too good where we zero out gradients, and not too bad where the generator can't train, right? So if we just honestly, like almost naively hike up the learning rate of the discriminator, it'll take those big steps and hopefully in a few epochs, learn that difference fairly quickly without, again, getting too smart, right? Because too many epochs with a small learning rate will result in our classifier becoming really good. A high learning rate with a few number of epochs will result in training faster, but maybe not converging, which is good for the generator. Okay, more problems. Any questions about this problem? Yeah, Shazam.
Why would have the gradients still be say when it zeroes out by that time, the generator itself would be good enough?
Good question. So that means that the discriminator, so by the definition of the whole GAN setup, that means that the generator is not good enough, right? Because if the discriminator can, with that amount of confidence, can tell the difference, that means we haven't fooled anyone yet. Like the generator is not good enough to fool an expert between real and fake images. Does that make sense? Yeah. Yeah. So yeah, so a little bit more on towards that question then. So like if in the middle of training, right? The discriminator can tell the difference between, hey, these crap images you made are fake. The generator can use that feedback to get better, right? But at the end of training, we only know if we've succeeded if the discriminator is always confused. The discriminator can still tell the difference somehow, and even worse, say that like an image from the data set is 100% real, your image is 100% fake. That means, in all honesty, your generator is not good. Like if that happens in training, your generator, there's no way your generator is good. Like you'll never have a case where your generator is good and your discriminator can tell the difference between both with 100% or like 99% accuracy. So yeah, I guess that's just, yeah, that won't happen actually. That's a better way to put it. Okay, so another problem. So again, maybe I shouldn't have skipped the game theory stuff. I mean, it's not that. Okay. Remember, so we can, from what I was saying earlier, we could frame this GANs problem as a min-max game, right? So again, remember, if you think of the loss value as almost like points, right? So again, like the discriminator wants to minimize that loss, but the generator wants to maximize the discriminator's loss. They have an inverse relationship, right? So that's what it means by min-max. So the discriminator wants to maximize the value, the generator wants to minimize that same value, right? So rock, paper, scissors is a min-max game for points, right? So if we're playing, I'm player one, you're player two, right? If I beat you, right, my score is +1, your score is -1 because you lost to me, right? So we can represent our scores through the same variable. It's just you invert yours and mine is positive. Ours are inverted from each other, right? Yeah. So as we're playing this rock, paper, scissors game, right? And let's say we're learning from each other, right? Um, so paper beats rock. Player one realizes rock is bad, switches to scissors. Player two realizes that and switches to rock to beat scissors. You'll notice that we have a loop, right? So if player one does rock, that beats player two scissors. Player two switches to paper. Well, player one will then switch to scissors, right, to beat player two. And then player two switches back to rock, right? So you'll see that we have these cycles. If it's turn-based and they're learning from each other, sometimes we have these cycles, right? So the analog to this in GANs, right? And I know this is, I've divided, so this is one epoch, that's another epoch, one epoch, another epoch, right? So these two are in pairs, this is another thing in pairs, right? So first, the generator updates, right? So let's say this is the generator's, is generating images kind of in this domain, right? So the discriminator then updates and it sees where the generator is positive. It just makes all of that stuff 0, right? Because it sees the fake images as fake and thinks, hey, like this stuff is mostly 0, right? Well, then the generator, again, is trying to fool the discriminator. So it just moves to the right, right? It just kind of hides in the shadow of the discriminator, right? So notice that like the generator has learned, right? Because again, all it's doing is like the loss function is not its similarity to p data to the data set. The loss function is how well it can trick the discriminator, right? So the generator is tricking the discriminator, right? So move to the left, the discriminator corrected for that, right? But the generator just keeps moving to the left. So if that's how it kind of figures out in its back propagation to beat the discriminator, right? Then we have a very bad generator, right? So this is the case in which a generator, this GAN setup might not converge, right? So the GANs could learn some policy which fools the discriminator, but in fooling the discriminator, it gets farther and farther away from P data. Shoots.
Then if this is like a possibility, why don't you just change the model setup to have a term that like tries to bring it closer to P data, like for your generator? Why not
Yeah.
just have like another regularization term that just like makes sure it doesn't go too far?
You are describing a way of doing that. Yeah. At the end, I have some strategies. Yeah.
That makes it better.
Yeah. That notion of distance is like one of the improvements on GANs. So GANs, I've explained them right now. So the kind of as they were proposed in their first paper are like really hard to train, like notoriously difficult to train. And they still kind of are, but the original GANs were like really bad for training. A lot of people just chose VAEs just because of how easy they were to train, and they just kind of ate the performance difference, right? But a little bit more on the third problem of GANs, and this is the most famous one. This one is called mode collapse, right? So remember in just basic statistics, right? If you have a distribution, right, of data, a mode is everywhere where there's a maximum, right? So if you have multiple maximums, so the same maximum value appears multiple times, you have, multiple modes, right? So you can imagine remember thinking back to like our analogy with GANs, right? So everywhere there's a peak or everywhere there's a mode, that's what so this is P of G, right? The probability that our generator generates an image, right? All these peaks signify that the GANs will generate this image, right? Mode collapse means when our generator only learns a single mode. So in other words, it learns to generate a single image. We did all this training stuff, all this optimization stuff, and then we see a generator that, it's learned to fool the discriminator just by outputting the same image. So you think of like back to game theory, right? Someone's like running the same BS like combo or like cheese move or something, right? So it just learns a single image, right? Instead of all of the images we wanted to learn. Okay. So again, yeah. So when mode collapse happens, all fake images look the same, right? So again, all of these fives are like different, we gave the generator different random vectors, random noise vectors. And for each random noise vector, it gave us back this exact five or variations of this five, right? So then the discriminator, um, because this five looks very similar to a five in our data set, it'll be like, hey, that's a fake five, or sorry, that's a real five. And then we fool our discriminator, right? So a solution to combat this mode collapse problem, right? Because a very common problem with GANs is this diversity intermediate value, right? Oh, sorry. And so what we do, right, is we take these output images from our GANs, right? So our CNN, like our convolutional max pool layers, crunch those numbers, right? And then right before we input it into like our neural network or activation function, right? We have these, non-human interpretable vectors, right? Right after CNN has parsed them, right? Well, you can imagine, sorry. Yeah, so we then take these non-interpretable vectors and then we combine them together in a certain way to create these diversity terms or this small diversity vector, which we then latch back on to the input to our CNN. So again, this diversity vector happens on like the batch level. So we have a batch, right, or like a data set of all of the synthetic images. We calculate the diversity vector, by inputting all of them into the discriminator at the same time, and then we, continue the discriminator's inference on each of the images individually. But now each of them have this green diversity vector term. Okay, so what is this diversity vector, right? So again, we take these purple vectors, right? Each one from a separate image from the generator, right? So we take each one of them and multiply them with a learnable matrix M sub I, right? So you can think of this as like a weight matrix, right? Just no activation function and no bias term, right? So just it's a weight matrix, right? And then, so if you have 4 inputs in, we have 4 outputs out, right? So yeah, sorry, I don't think that made much sense. For each input vector, we multiply the matrix and we get that red output vector, right? So for each of these red output vectors, we calculate the distance between all of the other output vectors, right? And then the diversity vector is the weighted sum of the output vectors with their distance from the other output vectors, right? So in other words, if all of these vectors are very nearby each other, right, the distances will be very small, and that will be represented in the diversity vector, right? So again, once we calculate this diversity vector for all of the images in our for all the mode collapsed images that we send to the discriminator, right? You'll see that the diversity vectors will effectively be the same if these images are the same, right? If these images are very similar, the diversity vector for each of these numbers will be very similar to each other. So then the discriminator, as it trains to tell real from fake, will notice, hey, like these fake images, sure, this stuff up top, looks indistinguishable from a real image, but this diversity vector portion, all fake images have these set of numbers. All fake images have a 1, 0.4, or 0.5 roughly, right? So then it just learns to use the diversity vector to tell real from fake, right? So essentially, by having this diversity vector, it forces us to learn different modes. Like it forces the generator to have different diversity vectors and therefore not output the same image, right? So that's why having this matrix T be learnable is very important, right? Because the gradients backpropagate through that matrix, incentivizing the generator to have different outputs. Okay, so if you guys have time and are interested in GANs for whatever purposes, I highly encourage kind of taking a look at these papers or these improvements on the GANs. So one of the first improvements on GANs was the WGAN, the Wasserstein GAN. And essentially, instead of using KL divergence, they use something called the Wasserstein distance. I'm not gonna, I don't have any slides left, so I'm not gonna get too much into it. But essentially, that rock, paper, scissors problem we had of never converging, it better directs that. So Shubes, that's not quite exactly what you're talking about, but it addresses the problem you raised. Style again was really cool. StyleGAN, I think I have these images from StyleGAN. Um, it's really it's just an improvement on like image generation. CycleGAN as well. CycleGAN is a larger architectural jump compared to these two. But anyways, if you're interested in GANs, I recommend taking a look at these three architectures. But yeah, that's pretty much it. Again, despite how finicky and annoying GANs are, in modern day, they almost, if you look at any image generation benchmark, they mostly like GANs based models outperform variational autoencoders based models for the most part, right? It's because they're um, generating like new images from the void essentially, right? As opposed to overfitting to the data set, right? That's why they do so much better than VAEs. Because VAEs just learn to reproduce the data set. GANs learn to like create images from nothing, right? Okay, that's it. I went a little bit over, my bad. If you have any questions, feel free to stay back. But otherwise, thank you for showing up. We have one more lecture this semester. Obviously no lecture next week. So the lecture we have coming back from Thanksgiving. I might do a poll once after that last lecture to see if you guys want another one because I think the lecture after the one where we come back, I think that's in finals. Is that in finals week? Yeah, so I don't want to give you guys another lecture during that time. So I'll have a poll if you guys are interested, just say yes, otherwise no. Our last lecture, by the way, is the third generative model, which are diffusion models, right? So they also generate images, but VO3, Dolly, what are the other big ones? Stable diffusion, it's got diffusion in the name. All those use diffusion, not GANs, not variational autoencoders. So yeah, see you guys in 2 weeks. Also, I'll have a coot next time, and I'll be shorter to accommodate the coot.